Okay, so Assalamualaikum and good afternoon. So we start our chapter 3 here. So the title is Solution of the Newtonian Viscous Flow Equation. So in general, we will learn about two basic flow, which call the Couette flow. So here, and the other one is the Poisson flow. This something like Poisson flow. So in this chapter. So this is a very basic one, and I hope you could do your own revision, finding what is the difference, what is the real meaning of a Couette flow and Poisson flow. But in general, I will tell here, Couette flow is more on flow refer to the flow between two plates like this. So it means that you have a fluid here, and then one or two of these plate is moving at certain velocity. Okay, it can be one of them is moving or both plates are moving. Okay, so and Poisson flow is more about a flow in pipe. So you have pipe there and you have fluid flow inside this pipe. So that is the Poisson flow. So the main difference here is for Couette flow, there are no pressure. We could say that because there are atmospheric pressure everywhere, so because it is open to atmospheric pressure, so we assume that pressure for Couette flow is equal to atmospheric pressure. But for Poisson flow here, as you know, when fluid moving inside a pipe, so they will develop pressure, because we could calculate the pressure by using the Bernoulli equation. So the main difference between Couette and Poisson flow is in Poisson flow, they will give you, or you need to calculate all the terms of dP dx, or the pressure here is exists. Okay. So I think you could download that notes, because I checked just now. Yeah, that notes can be downloaded. Okay, so we go for this one first. So for example, in this section, we will focus on Couette flow. Okay, here. Okay, and then we are focusing into these three situation where the flow produced by a moving plate. So means that one of the plate here will move with certain velocity. And another one is the liquid flow down an inclined plane. So means we have two plates like this, and then the fluid inside this plate, the fluid between this plate is flowing down, and then the flow between two stationary parallel plates. Okay, so it is mean that if you have the vertical flow, you have a vertical plate, so the fluid will flow downwards by gravitational force. So, and then we need to develop a few equations about that. Okay, first, I think you could see this diagram, and this diagram is quite common. So we just imagine that we have an inclined plate like this, and the inclined angle is theta, and then because we are focusing on Newtonian fluids, so means that the no slip condition will occur. So the molecule here will give you zero in velocity. So the velocity distribution will be shown like this. Okay, and then we imagine that we have a small particle here, as shown in the dotted line here, and then we need to determine the force, all the forces that act on this control volume, on this particle, and because we assume it is in equilibrium, so we equal all of that forces with zero. Okay, and then this idea is actually related with Renault transport theorem, as I mentioned yesterday. So first, we assume that We assume that we have one area like this, and then to make sure that we need to maintain all the element inside this molecule in its own in its current situation. What we did is we push certain forces like this from both sides to make sure that this force or this fluid will not moving outside. So and then so we found that the element that acts on this the forces that act on this element is first is pressure, mean forces that comes from pressure, and then forces that come from the shear stress here, and then forces that come from the weight. Okay, and then you already know that if we want to solve vector, because we have scalar and vector units, so when we want to solve a vector element, so we solve it according to its axis. So because the flow is actually flowing down like this, so we are focusing on this axis. Okay, I'm sorry, a phone call. So I think you already know about the existence of these three elements because we discussed it previously in developing Navistic equation. So now we will focus for each situation. Okay, so it's shown in the notes. So and then to make our calculation a little bit simple, so we take the control volume. The dimension of the control volume is delta S times delta Y and times unity. So means that we only pay attention on the height of this one. Okay, okay, this is the delta Y because we assume this is the Y axis and this is the delta S, mean the distance of the let's say X axis or the incline, the plane axis here, and the thickness of this control volume is equal to 1. So that's why we call it equal to unity. So as I said previously, in equilibrium, so we found that all the forces will give, the total forces will give you a zero value. So what we need to do now is we calculate all the forces. So we have the net for the pressure force is P times Y. So as you could see here, the height here is delta Y and the width here is equal to 1. So we have only P times Y. Okay, so and then we minus with the P plus dPds delta S times delta Y, and we could have this one. So this is just the common idea because we believe that the upper pressure here is larger compared to the lower pressure here because the flow is from the top to the bottom like this. So we do the calculation by this way. So and then we calculate the shear stresses. As you know, previously we learned about the viscosity. So the equation that might be related to this one is force is equal to tau A. So and then we have the tau plus d tau over dy delta y as, And then the area here is delta S times unity times 1 unit, because the width of this element is equal to 1. So here we assume that the top, the means the shear stress at the top here, it might be bigger compared to the shear stress at the bottom. So according to this free body diagram. So we solve this one, and then we get these terms, and then we simplify the term for the gravitational, the gravity. So as we know that we will only discuss force of gravity in S direction, means parallel with this plane. So you could have another component here. So I think you could imagine about this, and then we only take the component of S axis. So we have a weight times sine theta. So however, we could write as weight is mg, and m here can be simplified as density times volume. So and then that's why we write as rho times rho times delta S and delta Y, because delta S is the length of this here. So and then delta Y is the height of this one, and the width here is equal to 1. So we just have a unity unit here, and then this is G and this is sine theta. So and then we change the terms of sine theta here, because we assume that okay, so we have the notes here. So because we have this is the datum, so if you have a angle here, so it will become minus z. So and then it's if you have sine theta here, it is equal to minus dz over ds. So and then we substitute all the value here, means we add this value with this value and also with this value, and then we equal to 0, and finally we can write down as this term. Okay, so and if you do this one, like it means you summing all the forces to 0 and you divide into delta S and delta Y, so you will have this equation. However, for this term, okay, this term, if you expand this one, okay, please write like this. So you have dp over ds plus gamma dz over ds. Because the term of gamma here, or specific weight, or rho times g, so it's we assume that it is a constant. So because we assume that it is Newtonian and it is incompressible, so means the density here is not changed, so it it's not affected by the changes. So mean we don't have the d rho or dz. Okay. Okay, so and then we have terms here. Okay, we have d tau over dy here. As we know that shear stress, okay, is telling here, so shear stress is mu du dy. So and then we substitute the value of tau here with the here. So we have d over dy with mu du dy here, and finally maybe we could write as d square u over dy square. And then we bring, because the mu here is a constant, so we bring to the right hand side, so we have the term of mu here. Okay, so this is just simplified the rho g and the gamma here. So this is the specific weight, the gamma, or the rho g. So I think I hope you could understand this because I simplified a little bit. Okay, so means that this is the basic equation that you should know when you have a fluid fluid that exists between two plates. Okay, you must remember that we are using plates. We are not talking about pipes yet. So we have a two plates, so we could have this equation to start our calculation. Okay, so for example, we have this condition. So this is the condition number 1. So this is a very basic when we have a flow produced by a moving plate. So for example, we have two plates here. One is fixed and one is moving. But maybe you have a condition like both plates are moving, or one or two plates are moving with two different liquid between these two plates. Okay, it's depend on the question. Okay, so and then to simplify this calculation, usually people will say that it is no pressure gradient, because as I said, there are many assumptions. One of them is because we assume that all of this is open to atmospheric pressure, so the pressure is now equalized with the atmospheric pressure, so it is equal to 0. So means that we don't have any dP over ds or any terms related to the pressure. So and then because we are focusing on axis S only. Okay, so means that we don't have any value of dz ds. So we are only focusing on y here and s only, mean y, x, and there are no z. Okay, so we could previously we say that all of this term is actually equal to 0. Okay, so means that after we change into this one, so we assume that this is equal to 0, because we assume that the pressure here, there are no dpds, and then there are no dzds. Okay, so I hope you could understand this one. So because we don't have dpds and we don't have dzds, so this equation is will equal to 0. So now we have d square u over dy square is equal to 0. So and then what we need to do is, okay, so this is the idea. We integrate from the basic free body diagram. However, we also can do this evaluation by using the Navier-Stokes equation, because we will use you are introduced with a Navier-Stokes equation. So this is the Navier-Stokes equation. So first thing that you need to do is you need to know what axis that you want to take. Okay, because of this situation, it is the x-axis. For example, if you assume this is an x and this is y, so because we are focusing on x-axis, so we take Navier-Stokes equation for the x-axis. So this is the full term of Navier-Stokes equation. So and then we try to simplify our terms. So this simplification is actually depends on the situation. Okay, normally we are doing this is only one dimensional, because we assume that we assume here that molecule here will only flow in x direction. So means that the molecule will not go up, and means that the molecule is not going like this. So means that there are no velocity component for the y. And again, if this plate is in 3D, we assume that this molecule is not moving also in z axis. So we just assume that this molecule is moving on the x-axis. That's why we could simplify that the velocity of v here and also the velocity of w is equal to 0. And then we could say that v here is 0, and then we have a w here is 0. So and then normally when we want to analyze something, we will take condition as steady state. So means that there are no changing of velocity in terms of time. So it is means like So it means that if you have molecule here, so and then after certain time, okay, if we check the velocity for this point, so the velocity is remain constant. Okay, so means that the velocity is not changed with this time, so we could take that du dt is equal to 0. Now the value of here is 0. Okay, so and then we assume that because we don't have a pressure gradient here, so dp dx is equal to 0, so we have a 0 here. So and then we assume that it is a fully developed flow, so the value of du dx is equal to 0. So we have a du dx equal to 0 here, and also du dx equal to 0 here. So because there are no motion in terms of z-axis, so we have du dz is also 0. So and then, okay, for du dx equal to 0 here, it doesn't mean that the velocity of u is equal to 0. You need to understand that. We say that du dx is equal to 0 means there are no changes of velocity of u in x-axis. You need to understand the meaning of du dx. So means that this is an axis. So the velocity at here and the velocity at here is actually remain the same. So means that there are no gradient, there are no increment, there are no decrement. So the gradient is 0. Okay, that's how you need to understand about du dx equal to 0. Okay.
Right, which means the velocity is constant, isn't it?
Yes, the velocity is constant.
Okay.
Okay, you need to understand, because previously in my previous note, I say you not only to have you need to have capability to solve mathematical terms, but at the same time you need to understand its meaning, its physical meaning. Okay, so and then because we are focusing on x-axis here, so means that the gx is not exist because gravity is act on the y-axis. So and then please be careful, because some students, they easily make this term is 0 because they assume that the rho is 0. So the density is not 0. Okay, so because of this one, okay, we could cancel this density from the right hand side and left hand side. So the effect of density is now is negligible. Okay, because sometimes if you assume that the density is 0, it will influence another equation, because some equation, because in fluid, density and viscosity is very important. You will need these parameters again and again. Once you assume that density is 0, so mean in another equation you will put density is 0, so that will ruin your calculation. Okay, in this situation, you must alert that, okay, the simple one is the row here can be cancelled off, and the value of g is not exist. So again, if we makes evaluation by using the Navistic equation, so we will get du dy is equal to 0, because here in your left hand side the value is 0, because all of this term is 0, then this value is 0, then you could bring the mu here to the left hand side and it is also equal to 0. Or means that to get mu times del square u over del y square is equal to 0, we cannot say that mu is 0. So means that del square u over del y square must be 0. That's why after we simplify our Navistic equation here, so we could say that del square u over del y square is equal to 0. Okay, then to solve this one, as you know that we still have terms in differential form here. So we need to do the integral. So we need to integrate this one twice, because the differential power is 2. So we need to integrate it twice. So what we need is we need to get the boundary condition. So the boundary condition is showing like this. And how to get this boundary condition, actually you need to refer to your diagram here. So for example, if you have a diagram here, because it is not worth for you to remember all the boundary condition, because boundary condition is changing every time when the application is changed. Okay, you need to refer to your diagram here, and boundary condition is the condition at the boundary. It reflects its own names. Okay, so means that this is fluid. So the boundary of fluids mean the the place or the location where this fluid contact with other solid. So means that this is the boundary of this fluid. So here we could write as, if the y here is 0, so it will produce u is equal to 0. So this is the boundary condition at this point. And the boundary condition at this point is 1, y means the height here is equal to L. So this is L. Okay, and then the u will equal to capital U. Okay, in my handwriting, I will draw U with bar like this to show the capital U, because it is might be it is not easy to differentiate between small u and capital U. That's why I write like this for the capital U. So this is the capital U. Okay, why the velocity of this molecule moving with capital U? Because this molecule stick very hard on the surface here, because there are no slip condition in this location. Okay. Okay, so I think you could do this, because I already show you how to differentiate it 2 times. So if you do this by using this boundary condition, so you will have small u is equal to C1 y plus C2, and then we use the boundary condition. We do the simultaneous solution, which could get that small u small u here means the velocity for each molecule here. Okay, and the capital U is the velocity of the plate. It also reflects the velocity for the highest velocity here. So you could get U is equal capital U y over L. And then if we substitute with this one, okay, so we have U over U, capital U y over L. And then from here, we could calculate the value of du dy. So it is equal to U over L, because we are integrating single y here. So and then it's become 1. So we only have U over L. So we substitute the value in tau here. So we get tau is equal mu U over L. So this is the basic idea that proposed by one French scientist named Couette. So we call it as a Couette flow. So this is for the condition where one plate is moving. So this is just example I take from the textbooks. So for example, if the fluid between the plate is SAE 30, lubricating oil at T equal 38 degrees Celsius, the plates are spaced 0.3 millimeters apart here. So the upper plate is moved at velocity of 1 meter per second. So what is the surface resistance for 1 meter square of the upper plate? So the surface resistance here is actually the force that you need to overcome according to the existence of shear stress. So we know that tau is equal mu du dy, and u dy can be calculated by using u over L. So we substitute the value, so we get it's 333 Newton per meter square. And then to get the force is tau times A, and A here is 1 meter square, so the force is 333 Newtons. Okay, so we go for the second situation. So for example, we have, so this situation called fluid flow down an inclined plane. So this is condition number 2. So here okay, the difference between condition number 2 and number 1 is for condition number 2, the fluid move because they are gravitational force. So in condition number 1, so the fluid move because you pull upper plate with certain velocity, so it's trigger the motion or the flow of that fluid. So again, here we assume that okay, the height, the depth is d, and then we have the pressure is also constant. So there are so many assumptions. One of the is because we are doing in atmospheric pressure. Okay, so and then we take is the dpds is equal to 0. So and then we have this one. This is from the previous notes. Okay, before we analyze this situation, I explain you the equations. So we get this equation, and suddenly, and then we say that there are no dp ds is equal to 0, and then we could simplify about the p here. So and then it's become negative y over mu sine theta. So about the negative here, it is about the axis of the gravity, because you know here the mu here is rho g. Okay, so and then so we assume that we have if gravity is taken like this, so and then we could substitute it into these terms and also these terms. Okay, so and then we assume that our negative dz, we have a dz here is negative, so we could have the negative value here. Okay, as you know that the ds dz, okay, because the condition is the fluid is moving downwards. So again, we will do our integration using this equation. So we have boundary condition when u equal to 0, y equal to 0 at u, at y equal to 0, u is 0, and at y equal to d, the du dy is equal to 0. So here the tricks, the meaning of this one is actually, okay, if you see this one, okay, if you see this one, we could say that at this condition, mean at y equal to d, at y equal to d, so usually we will write u is equal to capital U, okay, based on our first, in this situation, we know exactly that the velocity at this height is capital U, but in this situation, we don't know. So we cannot simply say it's equal to u, but the best way is to say that du dy is equal to 0. So the du dy means the changes of u on y-axis is 0, means there are no changes of u in y-axis. So the idea is you could imagine like this. Okay, so when this molecule reach its maximum velocity, so let's say it is 5 meter per second, and then all the molecule here will flow at the same velocity, which is 5 meter per second. So means that the gradient along this y-axis is actually 0. Okay, that is the meaning of du dy is equal to 0. So and then what we do is first we do the first integration here, because we have by the power of 2 here, we do the integration here. So we put the second, we put the boundary condition. So and then we integrate. We have this term after we do the first integration. So here we use the second boundary condition. So now we have a du dy is equal to 0. So we could replace it here. Okay, so So we could get the value of C. The constant is gamma, which is rho and G, gamma D over mu sine theta. So finally, we could substitute in this term because previously we have these terms here. So we substitute this constant into what we have here. So and then we could have full terms after we do the second time integration. So we have this one. So and then we have another constant here, and we could imagine that at u equal to 0, at y equal to 0, then there are no constant anymore. So we have a c equal to 0 here. And then finally, we could say that the equation can be written as u equal gamma sine theta over 2 mu 2yd minus y square. So it can be might be simplifies like this. So this equation actually, in this equation we use nu. Nu is the kinematic viscosity and mu is dynamic viscosity. So I think you could you already know that the relation is mu is over rho nu. So and then that's why in this term they show in the gravity, because the gamma here is actually the multiple of rho and g. Okay. So and then we could calculate the u maximum. So we just substitute in the equation for this condition. For example, to get the maximum, so we assume that u is maximum when y is equal to d. So we substitute in this equation. So we substitute y equal to d here. So we get u maximum is equal to gamma d square over 2 mu times sine theta. So and then if you want to calculate the discharge, okay, so discharge here is actually flow rate. So the idea is Q equal AV. So the Q here, okay, so we are integrating U times dy. So U here is the velocity, and dy here is actually represent the A, the cross-sectional. So it is imagine that, for example, we have a plane here, okay, and then we have a fluid here, okay, with certain volume like this, okay, because the width here is equal to unity, is equal to 1, so we just assume that we time with the y only. That's why in that equation, we only have a dy here, because actually it is reflects to dy times 1 unit of width. Okay. Okay. So and then if you do this everything, you could have this one. So and then we could say that after we get the Q here, okay, we could divide with the cross-sectional area again to get the average velocity. So what is the difference of this V and this U? Okay, both are velocity, but for this small u, okay, it's reflect. So we have a plane here. So it's reflect the equation of the velocity distribution for that fluid. Okay, so means u here for each location of y can be determined by using the equation of uy. Okay, so and then but for this capital V here, it's actually the average velocity. So we just assume to ease our calculation, we neglect the velocity distribution here. We try to convert this velocity distribution into an ideal velocity, means all the velocity is actually same. So this is the idea or the physical meaning of the average velocity. So and then for the slope here, S theta, in some textbook, they will give you in tangent theta. So I think you can imagine that, because we are talking about water flows down naturally. So means it needs some inclination of the plane. So if your plate here is horizontal like this, so the water will static. They don't flow, because water flow from the higher location to the lower location. So the angle here, okay, so means that the height here and the length here is quite important one. So the theta here is, some textbook they will say that theta here is equal to tangent theta. So that's the meaning of this one. Because sometimes we could assume that the sine theta is equal to tangent theta. Okay, so if you evaluate this one, if you read a lot of textbooks, you will find that in some textbook they will evaluate this one by using the idea of Bernoulli equation. So by Bernoulli equation, you will have that. I think you already know the equation of Bernoulli equation. So you have a P over rho G, you have V square over 2G, and then you have Z, the elevation. So the Z here, so it is equal to, with let's say this is for point number 1, and then it must equal to rho G for point number 2. Okay, so and then if you have a situation like this, means that if the thickness of this water is the same, so means the pressure is can be cancelled, because the pressure is atmospheric pressure. Because the thickness is the same, so the velocity is equal. So we change then the Z here, actually it is equal to plus losses actually, if you remember. So we have a losses here, so then the losses here can be calculated as Z1 minus Z2. Okay, so means the height here will contribute to the losses of the flow. So losses of the flow means that if, for example, if you connect your pipe, for example, this is, you have your pipe here, okay, and then you connect with hose, with the rubber hose. So if the hose is short, so the water that comes here is in high velocity. So the velocity is there. But if you connect the hose here with the longer one, so you will find that the velocity that comes out from the hose is slower. Why it is slower? Because there are losses. There are, means you increase the surface, you increase the surface of water, the hose, means water needs to contact with the hose surface. The shear stress occur, and that shear stress will resist the velocity. So means a part of the energy from the water need to overcome the friction on the hose surface. That's why if you have a longer hose here, so it will slow down your velocity of water. Okay, that's it. Yeah, that's it, the idea. So and then if we do the calculation of Renault number here, we found that if it less than 500, we call this fully laminar, mean 100% is laminar. And then if it's more than 500, so actually if it's more than 2000, so it will going a fully turbulent. Okay, so another similarity of this idea is an open channel, because we are discussing about the incline like this, and then you have a water on that inclination plane. So it is same like a conduit or like a drainage in your town. Okay, people not create drainage, might be at your house in horizontal condition. But if in horizontal condition, the water will not flow down. Okay, some people will increase it a little bit. So the way people increase it, people will increase the depth of the conduit. Okay, so means that if you land is flat like this, so people will create conduit is slope like this one. So that's why if you see a drainage, okay, at certain part the drainage is shallow, but at certain part the drainage is deeper. Okay, because they want to create an inclined plate. Okay, so this is quite simple. So we have the crude oil, we have the kinematic viscosity, we have the specific gravity. So please alert that specific gravity doesn't have units here. This is the kinematic viscosity. So, and then you have slope of 0.02. So, and then the flow depth is 6 millimeters, and then you need to calculate the Renault number. So, this is the equation. You can substitute everything, and then you could get the flow rate here. So, and then you could get that the Renault number is 1.63. So, because it is below 500, so we assume that this flow is laminar.